In this video, we'll run through another example of proof by induction where we organize everything in a table. So with induction, we're trying to show that a recursively defined sequence, which we see here with the pattern and the initial condition, matches a closed formula description of a sequence. So we're really just trying to show these two things are the same for all values of n. When we say we're doing a proof by induction, that means that the reader is agreeing to check that these two things are equal in order. So they'll start by checking that A1 matches, that A2 matches, and so on. So, and we can take advantage of that logically. So in the table, on the left-hand side, we're calculating the sequence recursively, and in the right-hand side, we're checking the closed formula, and then we're just putting a check mark if those two things are the same. So, so first of all, with A1, starting with A1, A1 equals 1 is actually given, oh, I don't want that color. A1 is 1 is given in the recurrence relation. And of course, the closed formula, when n equals 1, is 2 to the n minus 1. So it's not hard to see that those are equal. When n equals 2, we're in this row. So we have a sub 2 equals 2, a sub 1 plus 1. That's me reading this closed formula off up here when n equals 2. So if n equals 2 and I write down what that says, it says exactly what I've written so far. And so that's coming from the recurrence relation, that we have that step. And then the second equal sign I have here is telling me that I'd like to evaluate this, and the only thing I don't know from what's written there is a sub 1, but I know that because I can look up at the previous row. So that step is because I know that a sub 1, and I'll just mark that here. So a sub 1 is the same as 1. That's coming from the previous row. And of course, 2 plus 1 is 3. So on the other hand, the closed formula, when n equals 2, is 2 squared minus 1. And those are equal. So we'll do it again. Again, my first equal sign here is going to be because of the recurrence relation. And so if I read the recurrence relation, again, this thing up here, if I read this off with n equals 3, it'll say A3 is twice A2 plus 1. Now, I can look up what A2 is by just looking at the previous row. The previous row tells me that A sub 2 is equal to 3. And so now I have 2 times 3 plus 1, which is 7. So that's what I'm getting when n equals 3. And of course, the closed formula when n equals 3 says 2 cubed minus 1. And again, I can check that those two things are equal. So we imagine the reader doing this. They have to be told to do it at least the one time, but they could do it 3 times like I did, or 4, or 9, or 100 times. But at some point, we'll be able to intercept the process and say, let's let m represent the row number well, let me just lost track of my grammar there. The number of the row, sorry, it's the number of the first row that's not yet been checked. So there will always be some first row that hasn't been checked. And remember, when we say we're doing a proof by induction, the reader is promising to check them in order. So if row 100 is the first row that hasn't been checked, that means I know that the reader has worked their way all the way down to through row 99 and checked everything off. And so the last row that they did check then is going to be row m minus 1, and so I can at least describe what that looks like. The a sub m minus 1 is going to be some stuff from the recurrence relation. That's what that's going to look like. The closed formula, I can say exactly what that looks like, because that's just the closed formula when you use m minus 1 in place of n. And those two things have to be equal. Because again, just to make sure it's clear, that if m is the number of the first row that hasn't been checked, then this number, this row, the one before, has been checked. So whatever I got here is equal to that. So now I'm ready to check row M. And this is where it will pay off that when I was checking it for numbers, I broke this into two steps. The first step that we used when we were checking row M was we used the recurrence relation. And so if n is equal to m, then the recurrence relation says this. So we can look back up, thing here. If we read that off using an m in place of n, it says a sub m equals 2 a sub n minus 1 plus 1. So that's what I've written here. If I don't have a highlighter, I can say that's true by the recurrence relation. The second step that we did when we checked those things with numbers is I looked up in the previous row to figure out what a sub n minus 1 is. Now in the previous row, remember, I couldn't actually describe exactly what I got from the recurrence relation, but I was able to say exactly what I had from the closed formula, and we know that that row had been checked, so I could use either one of those things. So a sub n minus 1 is the same thing as 2 sub n minus 1 minus 1 by the previous row. And so now I'm off in algebra land. So if I distribute that through, that's just the distributive property. So I can just say that's algebra going on. And then I need to use my rules of exponents, which is why I had you review this stuff. 2 times 2 to the n minus 1 is 2 to the m. Minus 2 plus 1 is minus 1. So that was a rule of exponents that got used there. I'm pointing it out so that you know why I was having you review those things. So in the recursive calculation, I end up with a sub m equals 2 to the m minus 1. And of course, the closed formula we get by just taking the formula up here and plugging in the row number. And so the row number is m, so that's what the closed formula would be in this row. And so those are the same thing. And so the logic here is if the reader tells us what row they're on with this checking process, we can tell them without it mattering what row it is. I can walk them through exactly why the row they're on also checks off. So this argument would work for if the 100th row was the first one they're on, or the 1000th row was the first one on. The exact same argument would work.